Good evening, everyone. My name is Claire and my colleague Emma, and we're going to go through machine learning with Python. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. In other words, the machine learning enables computer to learn patterns and make predictions without explicitly programming it. Machine learning enables machine to learn by feeding them data so that they can learn from the patterns in the data. The second slide, machine learning has two types. The supervised learning, it is the type of machine learning where a model is trained using labeled data. Here, the model is trained on a labeled data set, meaning each data point is paired with its corresponding output. The model learns mapping between input features and labels to make prediction for unseen data. So the goal is to uncover the hidden patterns in the data without specific outputs or labels. So we have even the unsupervised learning, the type of machine learning where the model is trained using unlabeled data. And here we have the models in machine learning, and a model is a presentation of some phenomenon. A phenomenon could be a real-world process or a system such as predicting the weather, classifying images, and there are types of mathematics or statistic models. We have the deterministic model, where there is no randomness and it hypothesizes exact relationship. And it is suitable when prediction error is negligible. And we have the probabilistic model. There is randomness and it hypothesizes two components, which are here. Before that, it hypothesizes two components, which is the deterministic and the random error. The deterministic, this part of the model predicts output based on the inputs using a fixed predictable relationships. And the random error, the output is unpredictable. We have the probabilistic models, and like I've said, there is randomness in probabilistic model. The probabilistic model has three types. It has regression, correlation, and other models. Regression models are used to present the relationship between the dependent variable and an explanatory variable. And we have the correlation model. I'm going to just give the real life example of the correlation model. Like in financing, assessing the correlation between the stock market index and the interest rate. Like, for example, if stock prices rise as interest rate fall, they exhibit a negative correlation. Another slide. Here we have the regression modeling steps include the hypothesize the deterministic components, specify probability distribution of random error terms, evaluate the fitted model, use model for prediction and estimation. Those are self-explanatory. I know you can understand that. Then we have the linear and logistic regression. In linear regression, the relationship between the variable is linear function, and the logistic regression is used for classification tasks like spam detection, like email spam. Then here we have the KNN and parameters, where we have the parametric model, where you know which model exactly will fit to the data. And in addition to that, parametric relies on the predefined assumptions about the data. And one of the advantages, it requires less data. And non-parametric model, the data tells you what the regression should look like. And in addition, makes minimal assumption about the data distribution. We have some examples of the non-parametric model, like the K nearest neighbors, where the model makes prediction based on the closest data point. And another example, we have the decision trees, the model builds a tree structure by splitting the data to various thresholds. And we have the attributes for the iris dataset, which includes the sepal length in centimeter and the sepal, sorry about the spelling, but it should be sepal width in centimeter, petal length in centimeter, and petal width in centimeter. And here we have the algorithm, the KNN algorithms step. Calculate the distance between all the training model and the test point, finding the nearest neighboring by sorting these pairwise distances, classifying the point based on a majority vote. And here we have some of the KNN applications, like you can apply the KNN in text mining, like text classification. But before that, KNN is for both classification and regression tasks. About the KNN in text classification, let me give an example. Like given a new tweet, KNN can classify it as positive or negative or neutral based on the sentiment of similar tweets in the training data. And for the agriculture, KNN can be applied in crop and soil prediction. Like you can say the use case, predicting suitable crops, analyzing suitable soil types, or detecting diseases in plants. Then we have the pros of KNN. They are self-explanatory. I'm going to just read through them. It is easy to explain, simple to understand, and extremely powerful. It does not require any assumption on the data distribution. It is the first choice when there is no prior knowledge or very little knowledge. You can use it for both regression and classification problems. You can use it easily with multi-class datasets. And we have the cons, which are the disadvantages. The efficiency of the algorithm declines very fast as the dataset grows. It comes at a cost of making the prediction step relatively expensive. Every time a prediction is to be made, it searches for the nearest neighbor in the complete training set. It suffers from a skewed class distribution, meaning it is a specific class frequently occurs in the training set. Then it is most likely to dominate the majority voting of the new example. It can work if there are any missing. Then we have the feature scaling and data cleaning. Feature scaling is a method to normalize data so features contribute equally to model training. It has the techniques standardization and normalization. Standardization transforms the data to have a mean of 0 and a standard deviation of 1. However, normalization scales the data to fit into a specific range. Typically, like 0, 1, 0, -1, 1, like that. Then you have data cleaning. It's a process, it's self-explanatory. It's all about cleaning data. Process of handling incomplete data, outliers, like incorrect data. And we have the feature engineering, the process of creating meaningful input features from raw data to improve data performance. Then each steps, we have the feature selection. Now the purpose of the feature selection, to identify the most relevant features for the task, to reduce the dimensionality and improve efficiency. And some of the techniques you can use filter methods and wrapper methods. And we have another step, feature extraction, feature transformation. Feature transformation, its purpose is to extract existing features to make them more informative or interpretable. Let me invite my colleague to start from there. Thank you.
I'm going to share my screen. The types of machine learning. So be brief. So the types of machine learning, we have supervised learning, unsupervised learning, and reinforcement learning. So supervised learning, they're using labeled data. Unsupervised learning, they're using unlabeled data. And reinforcement learning, they're combining multiple models to produce a robust model. So in the supervised learning, we have the classification and regression. algorithms. So in classification here, we have data classified in two. So we have two data sets or labels. They may not necessarily be two, but they are classified into known labels. For linear regression, you're using linear functions, equations of a straight line, and we predict the line of best fit or data sets that are close to the line. Then clustering, the data is grouped into clusters or multiple groups that may not be necessarily known or unclassified. Then in reinforcement learning, we have different models collected together to form a robust, efficient model. So now we're going to proceed to ensemble learning. So ensemble learning is a machine learning technique that combines multiple models. So often learners to improve overall performance. So the models in ensemble learning are normally weak models that are combined so that you have a very robust model. Examples, we have bagging, we have boosting, stacking. So bagging, they're having independent models. For boosting, we are having sequential data models. So the key idea for ensemble learning is to aggregate multiple predictions and reduce errors and increase robustness. So then the out-of-bag error. So for example, as I'm going to explain in the bagging process, we're going to have data samples. So if the data sample is reduced and the sample is no longer the actual sample, so this creates an out-of-bag error. So this is a performance measure for models used during bootstrap sampling. So for example, if I have a sample and then I select an item and the item is repetitive. So for example, I have 1 to 5, and now I repeat 1, I eliminate one of the data items. So some items are not included, which creates an out-of-bag error. So the advantage is it increases the probability, it adds a probabilistic context to the data, increasing its predictability and randomness. Then bootstrap sampling. So this is a sampling technique where we introduce randomness in the model. So the process, we have a bootstrap sample should have the same size as the data set, and then the points should appear multiple times. So some data points should appear multiple times, and then the purpose is to train models with different samples, different data samples, so that you can provide an aspect of randomness in the model and reduce overfitting. So this would create an efficient and robust model. Then random forests. So random forests, these are multiple decision trees. Decision tree is like a procedure that directs you to a decision. So steps to create a random forest, you use bootstrap sampling to create multiple sets of data. You train the decision tree on each subset, but use only random subset of feature for each split, then aggregate predictions from all the trees. That's a procedure for creating a random forest. Then the pros and cons. So most of them are self-explanatory, but I'll explain a few. So the pros, we have the random forest, it handles large data sets. Remember, it's a collection of multiple decision trees, so it can handle large data sets. So it's robust to overfitting due to, remember, there is a feature of randomness in the decision tree. Remember, it was a collection of multiple decision trees, so there is an aspect of randomness in the decision tree. Performs well on imbalanced data sets. So that is an advantage, a pro of a random forest. Then the cons, it's expensive. Remember, now we have multiple data sets and databases, so it's computationally expensive, and this would require much computing power and hardware to carry out any data set involves a random forest. So it's harder to interpret than a single decision tree. So it also may struggle with sparse data and time series problems. So I'm going to contrast boosting and bagging. So bagging, it reduces variance by averaging prediction, that is purpose. And then this reduces bias. For bagging, we're reducing the variance, here we're reducing the bias. And then in the model training, bagging trains independent models without bootstrap examples. Boosting trains models sequentially. It accumulates the models. And the key techniques, we have random forest and bag trees. The key techniques for boosting, we have AdaBoost and gradient boosting. So error handling. So for bagging, we are going to average all model outputs. For boosting, you're going to give higher weight to misclassified samples. Then the risk of overfitting, it's lower due to averaging. Remember, we are taking the average for bagging, and then it's higher because we are biasing one side. So there is a higher risk in boosting. Then the support vector machine. So this is a supervised algorithm. It's used for classification and regression tasks. So it has a hyperplane that separates data points with the maximum margin. So it has a linear support vector machine, a non-linear support vector machine. It also has a soft margin and a hard margin. So in the linear vector machine, we are going to have data that is classified based on a linear function. But then in the non-linear, you're going to involve Kernel tricks to create a data sample using the support vector machine. So to contrast the support vector machine hard margin and the soft margin. So the hard margin, it requires data to be perfectly separable. So in the hard margin, you're going to separate data perfectly. Then in the soft margin, you have data that is not perfect. For example, here in the hard margin, for example, if you're carrying out an image classification, in the soft margin would be maybe filtering spam messages, or you could be trying to authenticate an image, a handwritten image. So you cannot easily distinguish perfectly the data samples. So the tolerance for noise, it can handle noise or overlapping data. So for the hard margin, it can handle noisy overlapping data. While this one cannot handle noisy overlapping data, while this one handles noisy and overlapping data. Then the risk for overfitting in the hard margin. So with linearity and regression, linearity, we have a linear function that we're using to generate the model. And then regression, we have a support vector machine regression. So we are classifying data based on continuous values. That's when we are using regression. Then nonlinear data, we are going to use Kernel tricks. So Kernel tricks are used when we have a data set that is clustered, that doesn't have specific labels. So when you're trying to project the data into higher dimensional spaces, so you're going to use Kernel tricks to do that. Then cross-validation. So cross-validation is almost like cross-proofing, like cross-checking. So you cross-check and prove that the model is actually working. So the method to evaluate the SVM performance is by splitting the data set into training and validation sets multiple times. So you're going to train the data set multiple times, and we're going to generate an accurate model. So the advantage, it reduces overfitting and provides an efficient model. So the model will be efficient. So we have a gamma value that is used in the radio-based function kernel, and then we also have the regularization parameter. The gamma value is used in the radio bias function kernel. So then we have machine learning and data standardization. So like previously when we studied in our high school, standardization is when you try to evaluate the mean to 0 and the standard deviation to 1. So this is going to create a normal curve with limits of a range of 0 and 1. So it's crucial for the SVM, KNN, and algorithm sensitivity. So the strength and weaknesses of the K-means algorithm. The strength, simple implement, and computationally efficient, works well for spherical clusters, scalable to large data sets. The weaknesses, it assumes clusters and requires a number of clusters. And then struggles with overlapping clusters. So that is all about the K algorithm. And that was introduction to machine learning. Thank you for watching.